Hi, happy afternoon. Am I audible?
Yes, ma'am, you're
My
audible.
voice is clear and you can see my slides? Okay.
Slides are not shared yet.
Okay. Give me 1 minute.
Yes, yes, yes. Yes, they are visible now.
Slides are visible now? Okay.
Yes, this it's visible.
So, happy afternoon, everyone. So, as Edna introduced, my name is Neelima, and today we are here to talk about thermal analysis. So, what is thermal analysis? And yeah, just technical glitch. Yeah. So what is thermal analysis and why it is important? See, thermal analysis is a branch or a group of techniques that study the properties of material as they change with the temperature. Now, why it is important to measure the properties of the material as they change with the heat? Because you can imagine any material in the world, whatever material comes in your mind right now, it is going to change its property with the temperature. Imagine a car. A car is made up of, let's say, its windshield is made up of a glass, its tires are made up of rubber, its bonnet is made up of FRP, like it's fiber reinforced polymer. Then its different components are made up of different metals or material. And you are using your car in CRG. Imagine if the glass windshield become opaque, metal FRP become brittle, your seats become hard, your seat cover become stiff, you are not able to drive your car. Is it happening? No, it's not happening. And the same car in CRG, where the temperature goes from minus 20 degrees centigrade, you can use the same car in Jaisalmer also, where the temperature goes to plus 50 degrees. Why? Because the material scientists who involved to design the components of this car knows in material a priori. What are the properties which are going to change with the temperature? He knows each and every component. And that's why he designed in such a way that your material, your car is stable in Siachinos and in Jaisalmer also. So thermal analysis. So what properties the material can change with the material? Can you, with the heat, can you think of it? These are the properties which can change with the heat. And you can measure them with the using of thermal analytical techniques. So what are the properties of interest which can be changed at the temperature with the heat and which can affect the properties of your components? This is the mass. Mass can change with the heating and you can measure the mass change using the technique known as thermogrammetry. Then heat of the material, the enthalpy of the material changes when you heat the material. You can measure the enthalpy change using the differential scanning calorimeter. The dimensions of the material changes with the heat. Every time I will not repeat with the heat because we are using the thermal analysis technique only. So every time you can measure the dimensional changes of the property using thermomechanical analysis. Mechanical properties of material also changes with temperature. DMA, dynamic mechanical analysis, can be used to measure that. Dielectric constant can be measured using the dielectric analysis. Electrical properties can be measured using electrometry. Optical properties can be measured using thermo-optimetry. Sound can be measured with the thermal soniometry. So as per the property of interest and the property you want to measure within your operational range of interest, you can use either of this technique and find out which property and how your material is going to change with the properties. So for first previous one. Yeah. Yes. Okay. So for experimental part, it's very simple. See, you want a sample holder to hold your sample. You want a sensor to measure the property of the sample. Now we have seen these techniques. So accordingly, which property is of interest, you will choose the technique and the sensor will change accordingly. An enclosure you need to conduct the experiment and a computer to control and process the things. It's a simple technique of the thermogrammetric analysis, simple instrumentation. But today, because of the time constraint and the limited time, we will be discussing two techniques in detail. thermal gravimetric analysis, which we call TGA in a common language, and differential scanning calorimeter, which is a TSC. That we'll see in a later. So thermogravimetric analysis. What is measured? It measures the amount of weight change as a function of temperature or time in a controlled atmosphere. You can measure the thermal stability of the material using TGA up to 1000 or 2000 degrees centigrade, depending on the furnace value. Sample size can vary from 1 mg to 10 mg. Heating rate can vary from 1 to 50 degrees centigrade. Even though your equipment allows you to heat at higher rates, in the slides coming up, I will show you why you should not use heating rate higher than 50 degrees centigrade. Purge can be nitrogen or air. And if you want particularly a different air, a different purge gas, you can use argon or whatever gas you want to use, but that should not decompose your material appropriately. Measurements are done by heating a sample at 10 to 20 degrees centigrade in a linear heating rate under the controlled atmosphere. And this is an ideal technique to use for the first thermal sample. Suppose for polymer industry, you get a sample which looks similar. All polymers look similar. By looking at the polymer, you cannot identify which polymer is what. So what do? You first find out the thermal, you do a TGA on that using the experimental condition which I showed you just now, and find out what is the degradation temperature of that material. So here, this is how a typical TGA curve looks. Y-axis is the weight per se and x-axis is the temperature. Now concentrate on the pink curve. As you heat the pink curve material, there is absolutely no change up to, let's say, 420, 30 degrees centigrade. And then there is a sudden weight change. And again, the sample stabilizes. So what is this? This is to read as onset of degradation. This is degradation pattern, and this is to read as completion of degradation. So here, if you see on the y-axis, the material, the weight percent remains 0, residue remains at 0, means that pink curve is totally degraded. Now let's concentrate on the red curve. If you see the red curve follows the similar pattern as that of pink curve, but if you see the residue, it is not giving me 0 residue like pink curve, but it is giving me residue 20%. Means the TGA shows that the onset is around 425 degrees centigrade, and the material is giving me 20% residue. If you concentrate on blue curve, you can see that there is one state which is below around 170 degrees centigrade. What does my TGA curve tells me here? That there is either water in my sample or some organic solvents which are getting evaporated below 150 or 160 degrees centigrade. Then again, there is this red curve, onset of degradation and completion, giving me no residue. Green curve shows me that my sample will be 2-state degradation. So this is how you can read a simple TGA curve, which gives you information about, is there any water content or volatiles in your sample? What is the degradation onset of your sample? Is your degradation, it's 2-state or 1-state? Is there any residue remaining in your sample? Very important information for the product design. Okay, next is, what is the typical applications of TGA? As I told you, TGA determines the thermal or oxidative stability of the material. It can study the degradation profile of the material. You can find out inorganic filler content, volatile percentage of there, if any, there, and plasticizer content of your sample. You know, inorganic filler, these plasticizers, these are the materials which are filled into the polymer to modify their properties. And for a manufacturer, it is very important to know what is the inorganic filler percentage in your material, or what is the plasticizer added in your material, because the properties, the final mechanical properties are going to affect because of the percentage of this inorganic filler or plasticizers. We will not go into the details of instrumentation, but just to give you an idea, there are 2 types of balances in TGA. See, TGA, what we are measuring weight loss as a function of temperature. So for measuring the weight, you need a balance, and for temperature variation, you need a heater. So there are 2 types of basic instrumentation, in which one is vertical balance and other one is horizontal balance. Vertical balance means the balance is directly connected vertically to your sample holder, and in horizontal balance, the balance is connected horizontally to your sample. This is very basic instrumentation I'm telling you, because the manufacturers have patent for their design. They have various ways of controlling the accurate weight measurement, accurate temperature measurement and all. This is just to tell you, this knowledge is sufficient for us because we are not going into the detail of the instrumentation. We will be going detail into the analysis of it. So what you are measuring, remember, you are measuring weight with respect to temperature. So in any thermal analysis equipment, it's very important that your instrument should be calibrated. Always your instrument should be calibrated, otherwise the information which you are getting will be wrong. So there are two types of calibration. Of course, temperature calibration. For the temperature calibration, your manufacturer has given, along with the instrument to you, Curie point standards. What is Curie point standards? These are the metal alloys which loses their magnetization upon heating. So there is sharp weight loss at the particular temperature. And this is a point to see whether your machine is calibrated for the temperature. So whenever you get TGA or you have a doubt about the degradation temperatures of your material, if you are getting you have some temperatures in mind and suppose your material is degrading before that or after that, just to take this Curie point standards and run a TGA, and you should see the standard sharp deflections at this 4 temperatures. This is the 4-point temperature calibration. And for weight calibration, always use a dry calcium oxalate. Please remember, I'm using the word dry. Calcium oxalate absorbs water. So you have to dry the calcium oxalate. And why calcium oxalate? Because the reaction for calcium oxalate up to 800 degrees are known, and the weight losses or the residue of what is to be remain is known. So take a calcium oxalate, dry it, and run it at either 10 degrees centigrade. Black curve is 10 degrees centigrade per minute curve. Now, for each step, the weight loss is known. For the first step, the weight loss is around 12.3, calculated weight loss, and TG measures weight loss as 12.26. You can see how accurate our TGA measurements could be. Second weight loss is known for the second step, which is around 19.2, and TGA measures it at 19.24. Similarly, for the third step also. Now you can see there are 2 curves I have shown purposely. One is black, one is red. So red is the curve of calcium oxalate heating in at a rate of 200 degrees centigrade per minute. This is to show you that if you increase the heating rate of your sample, the total behavior of your TGA curve is going to change. Weight loss will remain the same, because if you see by hitting the calcium oxalate at higher rate, instead of 12.26, I got weight loss is 12.39. And if you see the percentage, it is 12.3 and 12.4%. But if you see the TGA curve nature, my onset of degradation and curve nature is totally changed. Okay, one thing I want to mention here is that the slides which I will present during my presentations are either our own work or the work carried out at NCL or some application notes of these thermal analytical equipment manufacturers or from open literature, and I acknowledge all of Brian. So I have acknowledged the thing, but again, if by mistake anything happened, I'm acknowledging all the thermal analytical equipments which are available in the market. Second thing is that your baseline. What is baseline? Baseline is heating your sample holder without your sample up to the temperature range of your interest. And your baseline should not have deviation or any sample degradation or any step in the degradation. Why this is? Because a previous user might have left some residue or have some sample spillage on your heater, or some sample is oxidized and attached to the corners of your sample pan. That can happen, and that will vary. That will always play in your real sample behavior. Maximum you can have around 0.005 milligram of weight change in your sample is allowed in your TGA. This we have already seen, so I will not spend much time on this now. Now, operating variables that can contribute to the reproducibility. In research life, we always use the word reproducibility. I will say that I have checked my reproducibility of my sample 10 times or 100 times. So what are the factors that can contribute to the reproducibility of your sample? First thing is calibration. Second thing is furnace cleanliness. Otherwise, every time the residue of previous sample affect your TGA curve. Sample preparation. Always remember that your sample should cover the whole base or your sample holder. It should not be in a grain form. If you have a crunch of a polymer, cut it into the small flat sample sheets and cover the whole bottom of your sample pan with the sample, because it will avoid the thermal lag, and whatever onset of degradation you get will be the true onset. Temperature range. Always select a proper temperature range for degradation. Otherwise, you will select a range which are lower than the degradation range of your sample, then you will not get degradation. You will get only a straight curve and your sample will not degrade in the range which you have selected. Scanning rate is important because I've shown you what will happen at 10 degrees centigrade and at 200 degrees centigrade. And sample atmosphere, which we will see now. What are the factors that affect the TGA curve? See, these are previous were the operating parameters. Ramp rate, purge gap, and sample weight. These are the totally operator dependent parameters which can affect your TGA curve. We will see them one by one. Ramp rate, heating rate. These are the samples. Red is particularly heated at 10 degrees centigrade, blue is 20, and green is 40 degrees centigrade per minute. So if you see here, the onset of degradation, if you heat at higher degree centigrade, shift it to the higher. Actually, the sample of the degradation onset is around 355 and all, but if you degrade the same sample with higher degradation rate, you will get at a 400 degrees centigrade as a degradation onset. So always, if you want to find out the degradation onset, do a sample with the lower degree. This is a particularly very interesting and important for the research student, because you never know that the caretaker of the equipment has calibrated the instrument with what flow rate. Here I have shown you that the instrument is calibrated at the flow rate of 25 degrees centigrade per minute, and the student unknowingly ran his sample at a rate of 50 degrees centigrade per minute, which is the blue curve. See, when the sample is run at the flow rate of calibration, that is at 25 ml per minute, you get a proper degradation curve, which is a rate degradation curve, which gives you residue as 0%. Now, in a hurry or unknowingly, the next operator run the sample at a flow rate of 50 ml per minute. Concentrate on blue curve. See, onset of degradation had started at after 150 degrees centigrade. In fact, actually 350 degrees centigrade, nothing is happening to the sample. But because of the flow rate difference, the sample shows degradation at early. Degradation pattern is different, and you are getting negative residue over here. Just see the y-axis. Your blue curve has gone below the 0% residue. This is because the instrument is calibrated at different flow rate, and you are running your sample at different flow rate. You will not understand by looking at the scan only that what has happened. Why my sample is showing negative weight loss? That is because of the flow rate difference. Now, selection of a proper purge gas. See, I told you that we can do the TGA in an air or in a nitrogen. But what if my sample itself is reacting with either air or either with nitrogen? Here is an example of manganese. The sample is run in nitrogen, and manganese form manganese nitride when you're heating nitrogen. So you get a weight gain in this TGA rather than weight loss. So one start puzzling, why I'm getting weight gain? Because your sample is reacting with the purge gas. Simple, change the purge gas. And remember, when you change the purge gas, just take a baseline in the changed purge gas and see what is happening to the sample holder, and then do a sample in a different purge gas. So for manganese, not air, not nitrogen, but argon is the right purge gas, inert atmosphere. So you should little bit know about your sample also. And if you don't know anything about your sample is an unknown sample for polymer people, do in nitrogen and do in air also, and see if you are getting a difference in the degradation process. Again, As I told you that do it air also and do it in nitrogen also. The same sample we take in an air and in a nitrogen. So this is a carbon black sample, which we use for a fuel cell application. So when you do it in an air, the sample reacts with the air and you get, onset of degradation at around 160, 170 degrees centigrade where actually our fuel cell operates. And second, then again, there is two-step degradation and all and all. Again, if you see the negative wet loss. My sample stabilization is below 0 degree centigrade. That shows me that my purge gas selection is wrong. So when we do the same sample in nitrogen, get a proper scan rate curve, onset of degradation around 450 and the expected residue around 40% because this is what I can say, it's a catalyst which we are using, which is 40% field catalyst. So here, if you see, I'm getting residue as a 40%. So nitrogen is the best environment, proper environment, not best, for my fuel cell catalyst. Again, Edna Invention Center has purposely done this experiment. Excess sampling. See, for each balance, there is a capacity of a sample. You cannot wait 100 mg of sample on a 10 mg balance. Like this, each TGA experiment, TGA balance has its capacity. So here purposely we have taken excess weight loss to show you what will happen if you take the sample beyond the capacity of balance. You will end up with the curve where you cannot extract any information with that. But if the same sample weight, if you reduce this to the below the capacity of your balance, you can end up with a nice TGA curve where you can extract whatever information like onset, degradation, residue, what you want. So balance records the correct weight loss due to the right sample weight. So choice of the right sample weight is also very important when you do a TGA. These are the small tips to get a good TGA curve. How you optimize the TGA condition? Never purge balance with reactive gases. Sample pan within the range of balance. Heating rate should be appropriate. Do steady purge and cleaning the furnace always heating at 90 degrees centigrade in air. Best way, as already we have talked about, if your sample is too much volatile, then always cover your sample pan with the cover. Small pieces, as we have already told you about that. When you should do the calibration of the instrument, when the purge gas is changed, when instrument is relocated, when purge gas rate is changed and temperature range is changed. Most important for students that you should be able to find out the artifacts. You should be able to identify the artifacts in the TGA curve. You should not interpret these as an TGA events. See, there are many effects like buoyancy effect, where there is a density difference in the surrounding gases due to heating or gas switching. If there are buoyancy effect, then you always subtract a blank curve from your original curve. If you find the fluctuation due to the purge gas, sample is getting weight gain or decomposing volatile very fast, use a constant flow rate. If you have volatile decomposed samples, use cover sample with the lead add and avoid sample excess. This is very important to get a good quality curve. Weight losses in TGA curves are always due to decomposition, loss of water, combustion, vaporization, evaporation, and weight gain is due to the reaction of gases substance with the purge gas or absorption of gases substance on the sample, which are like a charcoal or they absorb gases on their substrate and then you get a weight gain. I showed you in case of nitrogen. Which is manganese. Oh yeah, manganese also. Accuracy of TGA curves, which we have seen in calcium auxiliary sample, we will not spend time on. So application of TGA in real life. You don't get only onset of degradation and degradation temperature and percent weight loss in TGA. You can use your TGA to find out the percentage of failure. This is important for research and manufacturing people also, because many times, the product properties may fail in quality control because of the failure change in the failure percentage. If a manufacturer changes make a small change in filler content, which are going to affect a large quantity in a mechanical properties of your material, but the manufacturer get a huge benefit in terms of monitoring because the filler is always expensive. Many times it's expensive. So what you can do if in your quality control, if one of your product fails from the same manufacturer, or if you change the vendor and your product is failing, first do a simple TGA of your quality control pass and failed sample also. How to find out the filler percentage in the polymer? This is the case when your polymer is 100% decomposing, means there is no residue. Your whatever residue are remaining is 0%. Then do a TGA of a base polymer and do a TGA of your field polymer. See, my field polymer is giving me 80% residue and only 20% weight loss. What does it tell me? The curve is telling me that in my sample is how much field? Can anyone tell me? Because material is 100% degrading. So 80% sample is filled. My material is filled with 80% filler. How to find out of filler and all? You can use the different techniques. But this immediately by TGA, you can find out whatever residue is remaining is of your filler. That was the case when your polymer is degrading 100%. Now, what if your polymer is not degrading 100%? The polymer itself is giving residue. So this is the rare case where your polymer itself is giving me 20% residue. And when you do a TGA of your polymer with the filler, it is giving me 40% residue. But now remember here, out of this 40%, 20% residue is of my polymer. So actual filler content is only 20%, not 40%. Right? So remember these small tips, but which will be helpful in manufacturing and in TGA, I mean in research industries. Also, many times a processor asks you that what is the time I can process your material. If you know the polymer processing, polymer first melts and then it is molded into the desired form, whatever form you want to for this application purpose. So processor always asks you the time. Up to what time I can safely process the polymer. So what you do, you do a isothermal TGA. That means heat your material at the processing temperature and hold it there with respect to time and find out how much weight loss is there at the particular, whatever, suppose a 4% or 5% weight loss is allowed for the processor time. Then you find out you can find out the processing time and you can safely tell the processor that yeah, up to 5 minutes you can process my polymer without the change in the properties. So you can use TGA as a tool to find out the processing times, not only weight loss and all. Now, okay. The next question is, can I find out what my material is? Because I'm telling you that this is the first technique you can use on an unknown sample. So this is a TGA of PP and PV sample. If you see onset of degradation, almost similar. Residue, okay. If you see degradation, completion, almost similar. So I cannot find out using TGA whether my material is P or P. You cannot identify what material it is. You can identify only onset and completion. Just remember, we will use it in the same slide in DSC. In case of a polymer blends, you can find out what blend composition is there, similar to the filler content of it. Then, as I told you, you can use TGA in QC also. This red is a good sample and blue is a bad sample. When you just do a simple TGA, which is otherwise similar, except in the onset of degradation. See, my bad samples are degrading at far below my good sample, and that's why it failed in the QC. You can use TGA in the QC also. Quick sample, people from oil industry can use to find out their assessment for the finding of the no time of the TGA, no time of the oil. If you are interested, I just quickly tell you what is the no time. No time is the test. No test is the test to assess the oil. What this people do, they do isothermal TGA of the sample and find out the weight loss at a particular time. This is suppose your benchmark. Then you get oil from different suppliers. You do a similar type of experiment. Experimental condition should be safe. You should not change the experimental condition. And you do a similar type of TGA curve. And at particular time of your interest, you find out what weight losses this material are giving. And you can then choose which oil to use and which oil to discard. So you see, TGA, you can use in quality control, choosing your material supplier here also. We have used TGA beautifully in defining the drying conditions of our electrode. This is the electrode which was failing in the fuel cell atmosphere. And when we did a TGA of that, we found that there is a huge weight loss below 150 degrees centigrade. And I told you that this could be because of the water, because of the organic solvents. So our drying condition of TGA electrodes were not proper, which is evolved by the TGA. And when we modify the drying conditions and drying time, this electrode gives us a beautiful current density. And you can see here that up to 300 degrees centigrade, there is absolutely no weight loss or a small weight loss, which is acceptable for fuel cell condition. So we can use TGA to optimize the drying condition of your product also, which we have beautifully used in the fuel cell conditions. Now, nowadays only getting information which we are getting for TGA is not sufficient for the final research. So you know what? There are now hyphenated techniques. What does it mean? That output of your TGA is fed to a different techniques, like FTIR to find out what elements are present, find out if TGA output, evolved gases are for GC, GCMS to find out to extract the more information from a single experience. But this is not topic for today's talk, so we will skip this. Okay. Now we will go to the second technique which we are going to discuss in a brief is differential scanning calorimeter. Early calorimeter was invented in 1780 by Bulakh and Lavoisier, where a heated body is placed in ice and the heat subtracted was proportional to the amount of water melted. But this was in 1780 and nowadays we get many sophisticated equipments. I think most of you are using it. We will go a little bit into the instrumentation after some time. So what DSC measures? DSC measures the differential heat flow between a sample and a reference as a function of time or temperature. Again, sample can be from 1 to 10 mg. Heating rate also can vary from 1 to 50 degrees centigrade and purge gas from nitrogen or air, whatever is of your interest. So DSC is the next technique, the next common technique, which is people are used in polymer. How does a DSC, typical DSC curve looks? Typical DSC curve looks like you get a glass transition temperature, you get a crystallization, you get a melting, you get a cross-linking, and then it decomposes. But remember, this decomposition stage should not appear in DSC, never, because all this decomposed material is going to settle in your DSC cell, which is a very hazardous and dangerous situation. So always do a DSC below your TGA, the degradation temperature. So for first, you know what you do? You take a TGA of your unknown sample, find out the degradation temperature, and always run a DSC 20 to 30 degrees below your degradation temperature, so that your degradation state doesn't occur in the DSC. You will never allow any material to degrade or decompose in your DSC cell. What DSC can measure? DSC can measure glass transition temperature, melting and crystallization temperature, heats of fusion and crystallization. You can study curing extent, curing kinetics using DSC. You can find out purity of your material. DSC is a fingerprint of material, fingerprint of polymers. It's a widely used techniques in polymer industry. You can study in details polymer blends, and you can compare products using a simple DSC. Again, DSC continue. I told you it can measure TG, I mean, glass transition temperature is TG. And TGA is thermogravimetric analysis, which we have discussed for 20 minutes before. So don't get confused between glass transition temperature, which always says TG and TGA. Okay. So DSC measures the first order transitions, which are melting and crystallization, which involves both latent heat and heat capacity change, and a second order transition, which involves only heat capacity change. And a DSC, total DSC curve, as we have seen, which is compromises of TG, glass transition temperature, crystallization, and melting. There are two types of, I will tell you basic types of DSC. There are two types of DSC, heat flux and power compensator. What does heat flux DSC do? Heat flux DSC measures the difference in the energy required to maintain both sample and reference at the same temperature. That energy change is measured in a heat flux type of the instrument. Here, the furnace is a one-block furnace. Sample holder can be aluminum, stainless steel, or platinum. And temperature controller measures the temperature difference between the sample and reference. And second is power compensation DSC, where there are different sample blocks for sample and reference. Differential thermal power required to maintain these two at an equilibrium is measured. There are separate heaters and they separate thermocouples for both. Again, sample holder or pan can be aluminum, stainless steel, or platinum. Don't worry about which DSC you are using, because the information which you are getting at the end is similar. Curves are similar, but one should know that basically there are two types of DSC, heat flux and power compensation. I told you that DSC is a fingerprint of points. Like every human have unique fingerprints, every polymer have unique fingerprints, unless and until you purposely modify. So here we have done this DSC long time back in 90s to show you that how it is fingerprints of polymer. See, LDP melts at 110, HDP at 155, PP at 160, PBT at 220, PET at 240, PP at 30, and PTFE around 350, 343. It's me. Do a TGA. Suppose you get an unknown polymer. How do you identify a polymer? You get an unknown polymer. Do a TGA, find out the degradation temperature. Do a DSC below 20 to 30 degree of degradation temperature and see the melting temperature. And you find out which polymer is that. This much powerful DSC and TGA combination. Okay. Again, as I told you, any thermal analytical equipment, calibration is very, very important. What are you measuring here? You are measuring temperature and you are measuring heat change, energy change. So what are the calibrated calibration should be? Well, your temperature should be calibrated and your energy should be calibrated. Again, your supplier will give you the standard known materials, which are pure metals, for which the delta H, energy of fusion, and melting temperature, TMs, are known. Usually, tin and lead are given with the instrument, which are indium melts at around 160 and lead at around 330. So you can calibrate your equipment over a wide range of temperature. So what you do, you take this calibrate supplied by your material, which are of high purity, for which the enthalpies of known, and these are the materials which are highly thermally stable. They do not react with your sample pan, they do not react with atmosphere. So do the calibration, take the small weight of your indium or lead as from the point of view of your operating range. Run the samples at a lower heating rate, let's say 0.5 or 2 degrees centigrade per minute, and find out its delta H and melting temperature. And if it is within this range of your reported range of your material, you can say that your machine equipment DSC is calibrated. And I strongly suggest that you should calibrate the DSC each after 3 months or 6 months. I used to calibrate it every after 3 months because many times because of the repeated cycles of heating and cooling, your temperature calibration little bit shifts with the modern extensive use of your equipment. So strongly suggest to calibrate the DSC machines every after each quarter. Always use an inert purge gas. Why inert? Because in air, your sample may react or oxidize, and you have seen in TGA there will be effect of oxidizing or reacting your sample with the purge gas. In DSC also you get similar type of reactions with the purge gas. So avoid that, use inert material. Again, in air, suppose you are purging your instrument with air. Air also contains some percentage of moisture. These commercial air cylinders or air if you use from the compressed air compressor always contain some moisture. Even though you have a good quality filters, getting a dry air is a little bit difficult task. And always the purge gas can remove your decomposed and sublimate product from this. Again, I told you baseline. Baseline should be absolutely if you see the my scale, it's a very small scale and my baseline up to 180, 200 degree or centigrade is absolutely straight. Baseline should be absolutely straight, ensuring me that there is nothing in the on my sample holder, my sample instrument is calibrated and absolutely clean environment. This is how a aluminum sample pan looks like. So you take a sample pan, you weigh the sample pan. I strongly suggest you that even though you have sample pans, taken sample forms that are the same box, you are keeping one sample pan with the lid and one you are keeping the sample. But your sample pan reference and sample pan where you are actually weighing your sample should be of same weight. Because DSC you are measuring the heat, which is joules per gram. So absolutely accurately or similar weight of your both the pans and accurately weighed samples. Also frame your sample in such a way that your sample should cover the whole base of your sample pan. It should not be craved or like this because this will give me a thermal lag. So this is a good sample which is cleaned properly. My sample base is fully covered with my sample. Accurately weighed sample pans will give you more accurate results. And avoid overweight also. DSC also, it will avoid the thermal. So in DSC, we are measuring glass transition temperature and melting temperature mainly. And crystallization kinetics or crystallization temperature and delta Hc will be automatically measured because if you cool the material, you will get delta Hc. So what are the factors in that affect your gas transition temperature TG? So heating rate, aging, hydrogen bonding, molecular weight of the sample, plasticizers, side chains, and polymer. So in the research student can find out or correlate with if you are particularly increasing the molecular weight of your sample, you can find out the TG, find out the TM, and you can find out whether your molecular weight is really increasing or not. We will see these factors one by one. I told you that aging affects the TG. This is the sample. Suppose many times we deal with the amorphous polymers, and when the material comes, you immediately do one experiment, many experiments you do, then you will keep your amorphous polymers on a shelf, and after 3 or 4 months, you again take the same sample, and if you repeat your experiment, you don't get the similar results. Why? Because your amorphous polymer age with the time. So how to find out where your material is aged? Because each material is half shelf life. After that, it starts aging. And amorphous polymers, amorphous material is in highly constrained, high energy state of the material. And any material always try to go in the lower energy state and want to settle and stabilize over there, stabilize it there. So age amorphous sample, how to find it out? Do a DSC. See, this is totally amorphous sample when you received it from the manufacturer. And with time it ages. How to find out aging? After TG, glass transition temperature, you get a melting, which is the indication of aging. And as you increase the time or shelf time, the melting temperature after TG is increases. And this shows you this is the most aged sample and this is fresh sample, amorphous sample. You can easily find out whether your material is aged or not by just looking at the TG. This is called enthalpic recovery. And there are n number of papers published on this enthalpic recovery. Again, today that is not the topic of our discussion. So I will not spend much time on this enthalpic recovery, but just to find out that amorphous material, whether it is aged or not, by looking at the TG, glass transition temperature, you can find it. Hydrogen bonding. If you increase the hydrogen bonding, you can see you have various varieties of nylons available commercially also. So as you increase the hydrogen bonding, your TG also increases. If you increase the molecular weight, your glass transition temperature increases. For the same material, If you increase the molecular weight by the order, your TG also increases with the 100 degrees, 200 degrees centigrade. A plasticizer decreases the TG. If you increase the plasticizer contains, so in some cases, let's say for nylon, water is a plasticizer. If you bring a nylon sample, keep it in on the oven in a rainy season, then the glass transition temperature, if the water content in your nylon changes, the glass transition temperature can vary from plus 94 to 60%. That is the huge effect of plasticizers on TG. Also the side chains, if you increase the bulkiness of the side chain, your glass transition temperature increases. Polymer backbone also, if you add on the flexible chains in the polymer backbone, your TG decreases. This is just to recall how DSC looks. Two types of experiment you can do using UTS. One is non-isothermal experiment, which is very common, and second is isothermal experiment. Non-isothermal, as the name indicates, is a temperature trap, and isothermal, it is at constant crystallization temperature with varying time. First, we will see non-isothermal experiment. What is the experimental conditions? You wear milligrams of sample, clean it properly, and you make a program. Heat a sample at a heating rate of 10 degrees centigrade above its melting temperature but below its degradation temperature. Again, cool it with 10 degrees centigrade and reheat with 10 degrees centigrade. What information you can get from here? From this analysis thermal, you can get melting temperature, crystallization temperature, heat of melting and heat of crystallization. Here we record the scan with respect to temperature. It's important. Why? It's important because it defines your processing temperature. Processor, by looking at this scan, find out that he should process material at melting temperature. Okay. Now, second is isothermal. Isothermal means what? As the name indicates, it's with respect to time. Here, you heat the sample above its melting temperature. Hold it there for 1 or 2 minutes to completely melt it. Only to predetermine crystallization temperature and record the scan with respect to time. What information you get? You get heat of crystallization, total crystallization time, induction time of crystallization. Induction time means what? At what time your crystallization starts and at what time your crystallization completes. Why this experiment is important? For a processor, the injection molding or a processor defines the residential time of its material in the mold. Because if you know the injection molding process, first the polymer is melts, then it is injected into a mold, allow that mold to crystallize, allow in the mold to crystallize to get a desired shape and the material get injected. So how time the material should be in the mold, that time can be found out by using this isothermal classification. So particularly in injection molding, it is very important to find out the crystallization time and crystallization temperature in the isothermal. This is how a melting process looks. If you get a sharp melting for a metal type of things, that is a pure substance, you can say. In polymers, we get this type of melting, broad asymmetric melting, because we have different molecular weights. So lower molecular weights melt first, higher molecular weights stay, and we record this as a melting temperature of polymer and this as a melting range of polymer. If you get melting like this is melting with decomposition, which is a very bad scenario for DSC. This is again shows me that there are impurities in my material. Again, the factors which affect our DSC also heating rate. In case if you increase the heating rate, your melting curve looks like this. I mean, Tm shifts to the higher degree centigrade in case of polymer. In case of metal, you get the similar melting temperature because in case of metals, you get onset of this melting as a melting. But in case of polymers, our melting temperature shifts to the higher degree centigrade and our crystallization curves also shifted to the lower with respect to the temperature. Again, sample mass. If you increase the sample mass, you get different melting curves and different crystallization curves in VC also. What are the factors that affect the melting? Again, hydrogen bonding. If you increase the hydrogen bonding, you get higher melting. Your melting increases with hydrogen bonding. If you increase the molecular weight, your melting again increases with the molecular weight. You know, many times the processor, we have seen that the effect of filler. Many times the processor add fillers in our material. We have seen that PP filled with the filler. So, similarly, if PP is filled with the filler, what is its effect? Its effect on the, it affects the crystallization. In melting, filler will not affect melting of the polymer, but it affects the crystallization of the polymer because those filler which you have added, that act as a nucleating agent for the polymer. It enhances the nucleation and you get at higher crystallization temperature, the crystallizing polymer crystallizing at higher temperature. Again, polymer can be used to study the blends. DSC can be used to study the polymer blends. This is the case of PPS HDP immiscible blends. HDP melts at 150. DSC shows that 150. PPS melts at 330 degrees centigrade. And my immiscible PPS HDP blend melt at showing me peak of HDP also and peak of PPS also. Similarly, in crystallization, HDP crystallization, PPS crystallization, and HDP crystallization. You can study the crystallization kinetics of PPS, I mean any blend system by varying the composition, temperature, etc. etc. Okay. Best practices for do DSC: small sample size, good thermal contact between sample and sensor, proper sample crimping, there should not be a thermal lag. Proper instrumentation calibration, there should not be a temperature shift. Proper scanning speed, because higher the rate, higher the melting temperature, higher the crystallization temperature. Purge gas should be inert. It should not react with your material. Avoid decomposition. Always run TGA before DSC. Otherwise, your DSC scale will get spoiled and will cost around maybe 8 or 10 times. What are the sensor sources of error? Same. Best practices can be a sources of error. If you don't calibrate, if you don't use inert purge gas, then that will be the sources. Again, like case of TGA, you should be able to identify the artifacts in DSC also. This is not the TGA. This is the sample pan dislocation. This is the mechanical shock, not your sample behavior. This is the cool gas entered into your cell. This movement is your sample movement in the pan. This is not a thermal event. This is the electric effect, power fluctuation. If you change the atmosphere, you get this weird behavior. And if you get your DSC like this is your sample sensor is contaminated. You need to change it. This is very important when you are using DSC. Or many of you might be using it. So this type of behavior, if you get in DSC, that is the time to change your sample sensor. DSC can be used in research life extensively because crystallization kinetics can be studied using DSC. You can find out the polymer crystallinity. You can record delta HF using DSC heating curve. And you can find out delta HF of 100% pure crystalline polymer. And the ratio of that can give you the calculation of percent crystallinity, which is a very, very important parameter in case of polymer, because polymer crystallities are going to affect the molecular, the mechanical properties of the ion product. Then this we have already discussed, H polymer. Again, you can study annealing cases, annealing studies. Particularly PLA annealing studies are very important because the crystallinity, you can control the crystallinity of any polymer by annealing the polymer. And you can study that using the DSC and you can determine or you can manufacture or synthesize the product of desired properties by annealing. Again, many times you get material from your manufacturer and you thought it is pure, it is totally amorphous. But if you do a DSC and you build a rare curve, then it is a totally amorphous polymer. But many times you get a small melting in your polymer, which shows that it is not totally amorphous. And just doing one DSC, you can find out whether your material is totally amorphous or not, your material aged or not. Again, I think Hoffman Weeks plots it a little bit deeper into that research. We will skip this slide at present today because of the time constraint. But if you are interested in that, you can contact me. I will tell you how to you find out how to get the Hoffman Weeks curve for any polymer plane or polymer pure polymer. Again, in real manufacturing point of view, how to use this. I told you how to use TGA in case of. Similarly, this is a processor problem. PP batch. The PP batch was showing some different properties, and in quality control, one batch passes and one batch fails. Then that person did a TGA. It did not give any information because the filler content was similar in that case. Then what he did, he did a non-isothermal experiment, which again did not reveal any information because the material was similar, the crystallization polymer, there was a small difference in the crystallization. But when he did the isothermal crystallization, the isothermal crystallization of the good and bad batch at the same temperature was the behavior was different. If you see the batch which passed, the QC was having different total time of crystallization, and the batch which failed was having total time of crystallization. So isothermal crystallization revealed a little bit deeper into the problem, and because the mold temperature, then the manufacturer rated the mold temperature and the batch used to pass. Similarly, same injection molding batch, similarly non-isothermal experiment did not reveal any difference, but isothermal temperature showed the difference in the crystallization time, and we could shift to the process. Lipstick, the interesting point, not only polymer industry, but the lipstick industry, the cosmetic industry also using DSC as a tool to modify or to find out their property, evaluate their property. Here there are 4 lipsticks. Usually women like to hold their lipsticks from 9 to 5. So if you see the DSC, let's concentrate on B curve, which starts melting at around room temperature, having comparatively broad, but I will still say narrow melting up to 70 degrees centigrade. Why that room temperature to 70 degrees point of interest? Because you can wash your face with a warm water also, and your lipstick should not go up. So these lipsticks will last even at if you wash your face for home. But it will not, it will have the patches in that. And if you see, concentrate on D, D starts a broad melting from above room, below, little bit below room temperature to 70, 80 degrees centigrade. So this lipsticks wears well and it will spread well also. So D is 9 to 5 degrees. So in cosmetic industry, pharma industry, polymer industry, everyone is using TGA and DSC as a tool to optimize their products. This is a similar case of injection molding. We will not spend much time on this on because I've already told you 2 or 3 reasons for that. I told you that you can study the curing of your epoxy resins using this. Here, remember, this is not melting, this is crystallization. Here, endo is up. So what you do, you take your epoxy resin, uncured epoxy resin, record a DSC melting, you get an exothermal. You find out its delta H. Then you cure your material at different time intervals. Again, find out its delta H. Now you know the delta H of uncured material and delta H of cured material. Find out its percentage by just taking the ratio of that. Do a DSC. Find out its TG, because glass transition temperature increases with curing. And you can then design a material. You can find out the time and TG of the material at which you want to apply or your application of the products are there. And you can always tailor-made your epoxy resin curing, or you can study the curing kinetics using DSC. Simple experience. Again, this is a problem where the one batch was failing and one batch of PP was passing in QC. In PP, polypropylene, always HDP is added to modify its impact. So one batch was failing, and when we did a DSC of that, you can see the HDP content of the batch which was passed was higher than the batch which was failed. Just one DSC told us that why the batch is failing, because the HDP content is different. Now you can find out the small HDP percentage using DSC. Because in TGA, you will not get this difference, because we have seen that PP and P are same temperature. No change in DSC. But in the melting temperature or the content also. Now, very important. I have seen in many recent students that they report their melting temperatures with 2 decibels. No, your accuracy of DSC calibration is not that much. If your DSC calibration, if you see the melting points of indium or tin, we always report it at 156.6. So you also report melting and TC as a whole number. Don't report it as a point. Always report set the experimental conditions, because we have seen that the heating rate, mass affects the TGA curve, affects the melting temperature. So while reporting melting, always state the experimental condition, state whether from first heat or reheat. For polymers, always report PM of reheated sample, because polymer remembers its history. So first heating melting of polymer always have the processing history. So melted, always second heat ka melting, you have to report in case of polymers. Heat of fusion, heat of crystallization value should be always up to 1 decimal, not 2 decimals. TG, last transition temperature, state the test method by which you are reported it, state the experimental condition, and always state which point you have taken, onset or midpoint. But because many people report TG as a midpoint of a step change, many people report it as an onset of mid change. So you always report it. What is your style of it? These are ASTM standards, American Standard Test Methods, to report the parameters which we are obtained from the DSC or TGA. These are the instrument manufacturers, major instrument players in this business, and I have taken many cases from their application notes. So I would like to acknowledge everyone in this slide for this, of course, my colleagues when I was working in NCA, Saroj, Sangeeta, Purvi, Nilakshi, all my colleagues, they have helped me a lot getting this information. I would like to acknowledge Venture Center staff, Venture Center Director, National Chemical Laboratory Director, TA and Punching Elmer Instruments, because I have used them for many years. And of course, you all are listening carefully for this. Yeah, thank you very much. And now, Edna, I think we can take question and answers if any time.
Sure. Thank you so much, ma'am, for that wonderful session. I think you have, I have no words. Right from the basics to the applications to the real life case studies, I think everything was touched on with much detail and finish. I think there are a lot of questions in the chat box. So if you want, we'll quickly run through that. But thank you for sharing all your insights with us. And this is all the real life case studies. I think they are very exciting to see that. So let me start with. So there is a question from um, Gaurav, and his question is, how can we interpret hydrogen bonding by looking at the curve given by DSC? So to be more precise, how pure drug and modified form of drug, which is formed due to the hydrogen bonding, how they look at these two different curves, we can state in curve is due to H bonding between drug and another material. So I think
Listen, Gaurav, you cannot directly identify hydrogen bonding. You will get the effect of hydrogen bonding on your material. Because of hydrogen bonding, we have seen that the TG increases. As the hydrogen bonding increases, TG increases. So what is the effect of your hydrogen bonding on your material? Increase in the TG. So by looking at the DSC curve, you find out what is changing your TG. And then you can correlate with that with the hydrogen bonding. If you're increasing the hydrogen bonding, TGA should shift to high.
Yeah. So, Gaurav, if you're still there, I hope that has answered your question. And I think in continuation to his only, he has asked another question, which he says is, how can TGA help interpret change in crystallinity? I think that, ma'am, you have already covered that
In
question.
TGA, we don't find crystallinity. You get only degradation temperature. So TGA is not the technique to study the crystallization. DSC is the technique to study the crystallization.
Yeah. So, Gaurav?
Yes.
Yeah. We'll proceed to the next question, ma'am. So the next question is, it's by Jamin, and the question says that I was wondering about transition temperature shift observed in hybrid material. So in DSC, transition temperature was say at a value of 50 degrees C, while in temperature, Raman transition temperature got deviated at a much higher value with respect to 50 degree C. So what could be the reason behind this kind of slow transition shift?
Basically, Jamie, this Raman technique and the DSC techniques are totally different, totally two different techniques. So you cannot compare the TG determined by totally different techniques. So as I told you, always you have to mention that which technique and what's the experimental conditions you have measured your TG. Those totally different techniques, because in Raman, I think you get like scattering things. I'm not much familiar with the Raman, but you cannot compare the TG by different material. Different techniques.
Sure. Yeah. Ma'am, next question is from Tubai. He says, how is TM different from TG?
Melting and glass transition temperature.
Yes,
Okay.
TM is different from TG.
Okay. So TA is a second or first order transition, which involves the latent heat and enthalpy change. And TG is a second order transition, which involves only enthalpy change. From the point of view of energy change, if you're talking. And in TG, you get only a one state. If you remember my DSC curve, it was only a one state transition, and melting, you get a D in that curve. Melting and TG both happens over a range of temperature, but it's a first and second order transitions. Hope this will clarify you or.
Yeah. So, by I hope that is clarified, because I think you need to understand this difference. It's a very, yeah.
Yeah. So, ma'am, can I ask one question? Like,
Yes,
yeah,
please
ma'am,
go.
like if you have a gel kind of samples and you put add water in that, and your glass transition temperature is like changing from, you can think from -57, it is going around -10. But if you think, so you are using that solvent in a application and you want to know, so if you freeze the solvent, when this solvent actually become liquid, so then you should report glass transition temperature, not the melting temperature.
Say it again, you are adding water to your gel.
I am adding
then you are freezing it.
So I am starting from -70. My according to TGA, my glass transition temperature is from neat solvent, neat gel. My glass transition temperature is -57. Okay, so if I add water, so as I add water, the glass transition temperature is going down because the hydrogen bond breaking this formation is happening. The glass transition temperature is going down, and I got only endothermic situation. So I want to use this solvent as a minus temperature application, so as a solvent. So I want to know, like, when my solvent is in a liquid state. So should I, like, in a water dilution situation? So should I report like glass transition temperature? Because when I see in different salts presence, my glass transition temperature is little bit varying. Like if I add in the gel 5 mole of water, it is like from -57 to -50. Then if I add 10 mole of water, my glass transition temperature is actually going to -30. So basically, I am interested in which temperature zone my solvent can work like that way.
But this is too specific question. I think we can take it separately. Okay. You can call me. I will give you my phone number or email ID to you. I think we'll talk separately. I need a little bit more explanation what exactly you are doing. I
Yeah,
need to understand what exactly you are doing. You cannot answer it priorly like what an explanation you are giving to me. We can
Okay,
take a
okay.
call for this, but definitely we'll take a call
Yeah.
for this.
Okay,
Yeah.
ma'am. Thank
So
you.
by what you can do is you can put an email to us with this query, and we'll be happy to connect with Neelima madam. You know, we can take up this query separately.
Okay, thank you.
Yeah, ma'am, the next question is from Tripurari. He says, how to do TGA of liquid resins and nanoparticles?
Uh, for liquid resins, you can cover your sample pan. Tripura. You can cover your sample pan. There are sample covers for the sample pan. You can do that in TGA. Nanoparticles, of course, you can put nanoparticles directly or some solvent in which you know the degradation of that solvent, and you can heat it in a TGA with the covered pan. Covering it.
Sure. So yeah, there are no more questions in the chat box. If anybody has any, we can spend another minute or so on, you know, you can just unmute and ask if you all have. Otherwise, then I have put our feedback form in the chat box. Please do provide us with your valuable feedback. It will help us improvise on the future, you know, sessions. And yeah, so if anybody has any questions, maybe we can just spend 1 minute or so taking that up. You can raise your hand or you can just unmute and ask. I think you're free to do that.
Is there any special lead or like pen required for the kind of gel kind of samples in TGA?
In TGA, I think for a gel, you can cover your sample pan. You can cover your.
I think, yeah. Ma'am, so Tripurari is saying, are there any special lid and pans for solid, for liquid samples?
For liquid
Are they
samples,
special?
yes. Tripura, you can contact your instrument manufacturer if you are using TA or Perkin Elmer. They will definitely help you because there are special types of sample with the lids. For both DSCs also TGMs.
Sure. Yeah. So yeah, I think with that we'll we'll conclude the session here. So Neelima madam, thank you once again for taking the time out for preparing this. I think ma'am is going to go on vacation, but she's still obliged and she agreed to take this session. Thank you so very much. And thank you to the Venture Center team also for arranging all of these things, and thanks to the participants for it was a quite detailed discussion. So for being patient, for coming up with your queries, and you can reach out to us for any of your thermal analysis requirements or any other analytical services that you may require. You can reach out to us. Our details are available on the website, and anything we'll be happy to assist. So with that, we'll wrap the session up here. Request you all to kindly drop the call. Just the Venture Center team will just now be there for some closing remarks. Yeah. Other participants, may please drop the call.